Hello. In this video, I will explain how you can use the Fracture Surface Analysis Toolbox, short FSAT, to analyze a single height profile. I just downloaded the FSAT master from GitLab and opened the file generate metadata, because the first working step I have to do in FSAT is to provide the right metadata for the case I want to calculate. FSAT is designed to handle different kind of surfaces to calculate the roughness. For this, we defined four kind of cases. So the case A is the case I will deal with in this video. It's a single height profile. But you can also have two height profiles. You can have a single surface, or you can have two surfaces to form a real fracture. So in this generate metadata file, there are all four core cases discussed in detail, which the required metadata that you need to provide. For this video, I just copied the first couple of lines. So I want to have a fresh start. I want to have the meta information for my sample, and the last two lines of the script where I save everything. I just copy pasted those two in a new file or new script I generated. So I called it gen metadata profile. You can name it any way you want. Just for you simplicity to go through all the information you need to provide to analyze the roughness of a single height profile. First thing I have to do is I have to decide how to name the metadata file that I will generate with this script. I decided to call it metadata profile.mat. And then I have to provide the actual metadata information for the profile. As I already said, it's a case A because it's a single height profile. I want FSAT to output figures, so I set the flag to yes, and I decided to have these figures in the format of a PNG. But you can decide of pretty much any file format you like for a figure. Everything that MATLAB supports with his export graphics function will be fine. To use the export graphics function, you need a MATLAB version of 2020A or later. You can give the sample a name, which is not obligatory, but what you need to do, of course, is providing the path to the raw data. In this example, I use the raw data that is provided within FSAT. So if you download the master, you get the folder test data. You can use this one, and from there we will use the profile top values. We can take a short look at this in the editor. So it's just two comma separated columns with the x and the set values. All right, so FSAT will always analyze the first column at x, the second value as set. And make sure that you have a dot in between, because this is important for MATLAB. And then you can have pretty much any delimiter you like. I will show you in a second. Here we have the comma. Therefore, in the metadata, if it's about the delimiter, I provide a comma, because this is what I used in this file. Before, I can also define the path, so where I want MATLAB to save all my figures and all my output. As you can see, the folder which will be generated in this main folder is not there yet. MATLAB will, or FSAT will generate this folder for you. I decided to have a test results order folder and then generate the profile folder within that one. I have to specify the units, the physical units in which the length and height are measured in my raw data file. So in my case, that was millimeters. And I can decide to cut off heights of my profile. And not heights, but length of my profile. So usually when you do scans, especially in 2D, the borders of the sample are not measured in high accuracy. There are a lot of errors, mistaken images. So you can decide, maybe cut off the first or last 3 millimeters in each dimension. So for this high profile, I didn't decide, or I decided that's not necessary, but I can do this if I want to by defining those two values. So independent of where your profile originally starts, it will FSAT will automatically shift the smallest value to 0. So you can decide, okay, if I want to cut off the first 3 millimeters, you just type in S3 here, right? So I said millimeters because I defined the units in millimeters. Depending on which units you're calculating, of course, you have to provide those values. Right, and I decided I want to have a length profile of 95 millimeters and ignore everything that's later than that. Most scanner software will operate on an almost regular space grid. However, because of measurement accuracy, it's not really top regular. But several roughness parameters require you to operate on regular spacing. So you need to provide the resolution of the spacing you would like to have. I recommend choosing spacing that is close to your actually scanner resolution. Make sure that there are roughness parameters which are dependent or sensitive to resolution. If you choose spacing significantly larger than your scanner resolution, FSAT will interpolate, and interpolated surfaces usually are smoother than surfaces or profiles with a higher spatial resolution. And then you need to provide the maximum and minimum bandwidth, which we'll use to determine the first exponent. How to choose those two values will be more clear when I show you the output and how you can optimize those ones. So the general workflow we recommend with FSAT is some kind of iterative procedure. So you start with some values, you look at the results, and then you fine-tune your metadata. You know, maybe you decide, well, okay, the first 2 millimeters don't look good, so we'll cut off 2 millimeters more, or things like that. Okay, but for first run, we would go with those values. And then everything you have to do is save this structure. So it's a MATLAB structure called sample. We save this sample structure to the metadata file we just specified on the top. Then we just execute this file, and we see that the metadata profile.mat file has been generated. All right, and it excludes this sample structure with all the information we just specified. Next step we have to do is we have to provide the link or the path to this metadata file in the analyze sample script. So this is the main file of FSAT, and there's the line metadata file name where we provide the name of the metadata file we just generated. Okay, it can be located anywhere on your disk. Here I located it for simplicity in the same folder, but that's not necessary. It can be, as long as you specify the path, it can be located anywhere. And then we just hit the button and start the calculations. You see FSAT will do some automatic output in the command line, as well as showing you some figures from time to time, because we said, yes, we want to have figures. And you can also see on the left side that it generated for the test result in there, the folder profile, and that now, step by step, this one is filled with figures and results, and we're already done there. Right. Short information about what's showing here, so everything went smooth. There is a check within FSAT that checks if you have all required metadata for the sample. It identifies the sample successfully as a 1D or as a height profile. That's what we've done. We provided all metadata that was required for that kind of case, and then it started calculating the roughness of the sample. Note that within one metadata file, you can provide several samples, so then it would continue this outputs for more samples. And then there have been some warnings because of the image displays, but we'll see that everything goes fine. If not, MATLAB will throw you errors there. You have provided probably wrong metadata files, or your raw data does not match the necessities that are required for FSAT. Now we'll take a look at the results order. So the first thing we can do is we can look at the raw data. This is the profile just plotted as the data as provided in the raw data file. You see, so there is nothing aligned to 0. So often scanners have some kind of strange measurement reference point in some kind of plane or location, which does not need to match your profile. So what FSAT does is it sets everything to 0. So now you see the same profile, nothing has changed. Just you see that the lowest point and the most left point has been set to 0. So now we can estimate the length of our profile, and we see the range of values, so something between 0 and 8 millimeters across a distance. We also see that there is a general trend, which often is the case, but usually a lot of roughness parameters are calculated based on the distance to the mean line. So what FSAT does it calculates this mean line. So now you see the same raw data as before, set to 0, but you see what the mean line could be. It doesn't go through 0, that's okay. And can calculate in the following the distance between each data point and this mean line. Then also we have to operate on a, as I said, on a uniform grid. So we can check how well this one went, looking at this figure, and we see we can't separate both lines because we are perfectly aligned on top of each other. If you see strong differences in there, you might want to adjust your spacing parameter in the metadata. So then we can now start looking at the results. For example, at the relative height. So here we see now the distance to the mean line we have seen before, and we see there's some positive and some negative values of the relative height. That's what we expect. We have our profile length. So now we already get a much better idea about how rough our surface is and how it looks like. And we can also some statistics. That was a mistake. So we can see here the histogram distribution of the distance from the mean line we have just seen here, and how often those occur. We see we have some very high, very few, very large peaks close to 1 millimeters or close to minus 0.7 millimeters. But this, we can also see, is that a Gaussian distribution or not? What kind of distribution is it? So it gives you some more quantitative estimation about that one. And then, of course, we can take a look at the results as a CSV file, which is kind of likely you might want to do that rather in Excel or any other kind of tabular calculation software, which can open CSV files. But within MATLAB, we can just import this workspace, import map file, and that provides everything that will be, and even more that's stored in this CSV file, because we get a table that's called results. We can open that one, and we get all the parameters that are calculated. So what each parameter is and how it's calculated, please look in another video or in the publication that is associated with FSAT. So we have, distance from the mean line, skewness and kurtosis of this distribution. All right, but it's not the topic of today. You will see that we are calculating or providing a lot of parameters with the mean value, the minimum value, the maximum value, and the standard deviation. For 1D profile, all of those values are the same, and there is no standard deviation. However, this becomes important when we look at 2D profiles, or 2D surfaces, or 3D surfaces, because then there is a variation of those along different profile lines and along different directions. So we will study those ones later. And here you see the first exponent, which is around 0.8, which is typical for that kind of sample because it was a sandstone profile, so this is what you would expect. But how can we determine those parameters? We can look at the respective figure, and there are a lot of different ways to determine the Hurst exponent. In FSAT, we use the method that we determine the distance between highest and lowest point along or per band, and we vary the bandwidth. Then you get in a log-log plot a linear relationship between those. However, you see that this linear relationship usually breaks for very large bandwidth or also for very small bandwidth. So what you can provide in the metadata with these first start, first end values is actually the logarithm of the bandwidth where you want to cut off for the linear trend. You see, I didn't cut off it in the lower part because that was all fine, but I cut it off around 4 because that's where I decided, okay, those points, that is not part of the linear trend anymore. Already have a little gap here, you have another gap here. So if I would include all those points, the interpolated line would be much lower, and we would result in a much lower first exponent. So this is a bit of kind of your decision where you cut off the fit of the linear, right? Great. You might also want to take a look, if you import this workspace mat file here, you also already get something called structure, and this provides you all the metadata information that we put in, but it also provides you all the results of the FSAT calculation. So you get our raw data. So it was originally 425 points because I set the spacing value a bit lower than what we had with the scanner resolution. I result in slightly more data points with the interpolation on my uniform grid. I get the set values for my interpolated line. I get my set values for the heights that I matched through interpolation through these uniform spacing. I get the relative height of my mean line. I can calculate my mean height, and I also get the deviation for my mean. So now you can generate your own plots, your own analysis based on those values. You don't have to do all these pre and post processing again, but you can directly operate on those ones. For example, if you want to start modeling, if you want to try other roughness parameters, or so, you can just now operate on those values. This was it for this video. There will be another video how to combine two height profiles, and then also for the other cases.